Well done, you made it to the end of the radiation topic. Let's have a look at nuclear density. So, atomic radius is approximately 1 times 10 to the minus 10 metres. At degree level, we refer to angstroms when we talk about this. In terms of nuclear radius, we know that's approximately 1 femtometre. But what that doesn't take into account is the amount of nucleons that there are in the nucleus, and that's something that we need to think about. Because common sense would tell us that as we add more nucleons to a nucleus, the radius would increase, because there's more nucleons in there, right? So, if we plot this as a graph where we did the radius against the number of nucleons, we get a graph that does this. That's the worst whistle ever. So, what we can see is radius is not proportional to the number of nucleons. And this is because radius is actually proportional to the cube root of the number of nucleons, which is what this shape is. So, if we were to plot radius against the cube root of the number of nucleons, hey, it's directly proportional. But what does that gradient mean then? It's a constant line, and it gives us this constant value, which is R0, which is approximately 1.4 times 10 to the minus 15 metres, so 1.4 femtometres. Now, you might be asked to prove this in an exam, given some data, and that's how you do it. You'd have an extra space, an extra column, you would cube root all of your values for the amount of nucleons, and then you would plot your graph, and your gradient would give you that value. If they are being proved to you in the exam, and want you to do it using the logarithm method, then this is what you would do. So we've looked at y equals mx plus c, so it stands to reason that c is equal to 0 here, and therefore, if you were to do the cube root of the number of nucleons, then that's the shape of graph you'd get, and your gradient is R0. The logarithmic way is to multiply through by logs. Okay, that brings the third down onto the same level and stops it to be a power. So you have log of R0 plus log of A times by a third. So y is log of R, so you plot your y values there. Log of A is your x, okay, which means that your gradient has a value of a third. The y-intercept would be the log of R0, and to find out what R0 is, you'd have to take an anti-log of that value. Now, the volume that each nucleon takes up, each individual nucleon, is approximately the same. Okay? Now, if we have a look that radius is proportional to the cube root of the number of nucleons, it would stand to reason that the cube of the radius is proportional to the number of nucleons. We know the cube represents volume, and therefore it's volume that is proportional to the number of nucleons. Now, if we assume that each nucleon is perfectly spherical, then the volume of the nucleus could be given by 4/3 pi r cubed. Now, let's substitute this in to here and do some elimination to show that nuclear density is a constant value. So, density is mass divided by volume, right? So, if we've got density, the mass of each nucleon, multiply the number of nucleons that there are, that will tell us the total number of nucleons mass. If we say that it occupies a sphere, okay, it behaves spherically in that level, then we've got this equation here. Now, what we can do is we can substitute this equation in here for this r down here. So we've got the mass of the nucleon times by the number of nucleons that there are, 4/3 pi, and then this substitution value, which is R0, A cube rooted. Not forgetting that the fact that the cube hasn't disappeared. So if we cube everything that's in that bracket, that third disappears, they cancel each other out. We end up having to cube R0. So we have A on the top, A on the bottom, they cancel each other out. And what we end up with is 3 lots of the nuclear mass divided by the 4 pi R0 cubed, which is a constant value. So your nuclear density is always 1.45 times 10 to the 17 kilograms per metre cubed. And you could be asked to calculate this in the exam. Be aware of how to do it. Dankeschön.